Hello, it is me, Hugo. So this one is anagram substring. Let's look at the original question. Is it here? Okay, here it is. So basically, I don't like the way it's worded. It doesn't feel like there's enough detail, and I mean, like, sure, an interviewer might say this, but I can ask the interviewer for more specifics. But in this case, I can't. So it just gives us it just basically says given two strings, A and B, determine whether any anagram of B occurs in the substring as a substring of A. So basically it's saying can string B be rearranged in any sort of way to be a substring of A. And the comparisons are not case sensitive, so we don't have to worry about the cases. So we can just lower them or uppercase them all if we want to. And then the input sizes will vary. This is what I meant when I said that it's not as specific as I would like it to be. It's not. The string sizes vary doesn't give us any information about like the minimum and maximum sizes of them. So yeah. And then we're given some examples here. It also doesn't specify whether spaces are important. Spaces are important, I'm pretty sure. Because I didn't work. I had to. I put logic in to include them, and it worked. So I'm assuming that if I took it out, it would probably fail. In both of my solutions. So yeah. And then here it just says that. So yeah. It gives us the base case where B has to be greater than or no, that B has to be less than A to be a substring, because obviously. So then it just does an if statement first before that for some reason. I don't know why they would have that. I feel like that's a thing that you would make other people do, or you wouldn't write a test case that would fail this to start with, but it's fine. My original solutions here, I first lowercase both of the strings that were inputted, and then I got the word count of the string B, so I got the character word count and I put it into a dictionary. So the goal was basically count the number of characters that occur, like count the individual characters in the string and in B, and then use a window, like a sliding window. So we're gonna use a sliding window that just goes through A, and that sliding window is gonna have a range of the length of string of the B string, and then we're just gonna compare the word counts for both of the B string to the A substring. So this means that if they have the same word count or character counts, that means that B can be rearranged or arranged in some sort of way that would be the same as A's substring. So if that happened, so in that case, if the word count is the same for both of them, or I should have wrote character count. It's fine though. Return true. Otherwise, we're just gonna increment both the left side and right side of the sliding window to move forward. And then if we get to the end and we haven't found a case to be true, that means there is no anagram in it, so we return false. So yeah, it's pretty simple. I could probably make this even more efficient than what it is already, because right now what we're doing is we're going through it, but we're getting the word count every time, so repeating a lot. We're repeating this operation. We're repeating this operation basically all the time, which isn't good because a lot of them have already been checked, and a lot of them will get multiple checks. So every character, I think, every character between. Okay, I don't want to start explaining math. But basically, the middle characters will be. The middle characters of A will be going through this function, the number of times there are, no, it'll go through the function length of string B times, and that's not really good because you're basically reconstructing a dictionary every time. So it's not ideal. I could probably fix it, but yeah. And then I could also probably make this more Pythonic and use a dictionary comprehension too. But that was my original approach. And then after a bit, I was like, okay, we did valid anagram before, and the approach for that I used an array of 26 integers that we just incremented for the first string and then decremented for the second string, and if there was ever one that wasn't 0, then we returned false, otherwise we returned true at the end. So I was like, this one's more efficient than the other solution because basically you're kind of keeping track of the word count or the character count, but you don't have to create dictionaries and any of that. You're just adding and like incrementing and decrementing values right here. The thing is that it's only going to consist of lowercase letters, and our example does not guarantee that because it has spaces. So because it has spaces included, I decided to go out of my way and try to implement it with those spaces. So let me copy paste this. Before that though, let's just look at the execution of this original one. It's 172 steps. It could probably be shorter with the optimization, with avoiding having to repeat this that many times for characters that have already been counted for. So yeah, it's 172 steps for this case specifically. I'll get into that a little bit more in detail later on, but this is my second solution. This one basically does the other thing, the valid anagram approach, but it uses them here. It's a lot less readable, a lot weirder, but it essentially just does what valid anagram does, but with the while handling the case of spaces, and also using a sliding window approach, because we know that the strings are not equal length, so we're gonna have to accommodate for that. But if I run this right now, it's gonna look a lot worse, and a lot worse, I'm talking a lot worse. 363 steps for the same input. So yeah, like what happens here? That's crazy. The thing is, my last check right here, you had to check all of the values inside of the array counter or the character counter, and it's gonna have 27 values. I just made the 27th value a left curly bracket with its space, because then that's the one right after Z, so it's just a quick workaround with it. But yeah, I had to go through the entirety of the array, every iteration. So it's going to go through 27 elements every iteration to check if there is a 1 in it or a -1. So if they're not all 0, then it's going to return. It's going to just break out and it's going to be false. But if it can go through the entire array without breaking and calling is anagram false, then it'll just return true, because then that means that we have no difference between the characters. So yeah, that's the problem here. It's with smaller inputs, basically this array, although it's constant size, it's still sizable enough that most normal size strings will be too small to be slower than this. So this solution technically does more steps for this case and all the cases that were provided to us as test cases, which are like 4. But yeah, so for like all of these cases, I'm pretty sure the dictionary one approach, the first approach, is better. The dictionary approach is what I call it. And then the array approach that I use for the second one, which is the second one, uh, that one works worse for these, but that doesn't mean that this one is worse time complexity, and that's an important thing to note. I don't think it's worse because so Python Tutor has an issue where you can't use large things, like very large requests will just be denied. So to get around that, I just made my own test because yeah. So I wanted to test it out with a very large string, and it's gonna be this: the quick brown fox jumps over the lazy dog times 22, and then we're just gonna what's it called? Concatenate A B C D E F G H I J K to the end of it. And then what we're gonna do is we're gonna have this be the string we're looking for, whatever. So it's not gonna find this until the end, and we're gonna use time it to basically run this a couple, no, not a couple, 1,000 times, and then we're just gonna find the average time that it takes for both of the functions to run. These are the same functions that are getting imported, so I just call it 2 and 1. So 1 is the dictionary approach, and then 2 is the other one. So yeah, and that's gonna be the test case. So when I run it right now, just gonna wait a second, and boom, the array version actually performs better. But if you look at my previous test, you'll actually notice that the array test did do worse than the dictionary for this example up here, and that was when I did str a is equal to, I think it was just a times something, and then it was like a times 150, and then a times 50. Okay, and if I run it, yeah, array average does worse. So it's for smaller strings. The array does worse, but for bigger strings, the array does better by a lot. So, like, if it grows a lot, the string will. If the string grows a lot, it'll just take a lot longer. Like, let's see. Let's change that to 100. I wonder how long that would take. I hope it doesn't take too long, but yeah, so it seems to be that the time complexity difference is there. Yeah, let's see. So the dictionary approach does take longer, but I don't know, I wonder if that would be fixed if I optimized it, and the array approach is just not slow as it once we get to the bigger strings. So I'm not sure how to feel about this. It's a very cool problem though. I like it. I like it a lot. It's very interesting. The this one I'm pretty sure is O of the length of both strings multiplied to each other, so kind of like an n squared thing going on here. It might even be more than that because I'm doing splicing inside of a while loop. No, wait. Yeah, I'm doing a while loop and then splicing, and then within that function call that's getting passed in, we're creating a dictionary each iteration. And then we're checking if the dictionaries are the same. I don't know how much that is. What is the time? What is the time complexity of checking if two dictionaries are equal? Not interested. O of n, where the number of key value pairs In worst case, for number key value pairs in the first dictionary and the number in the second dictionary. Yeah, so it would basically be another call within the while loop already, so I don't know. And then with this one, what would it be? Let's see. So the thing is that we have a constant of 27 here. And although 27 is still large, it's constant technically, kind of. I don't know, would that count as constant? I mean, it's fixed size. It's not going to grow as the input grows. I think that's the definition, I hope. I'm pretty sure. I haven't taken a DSA class. Uh, I think that's what it means. Wait, is time complexity how what was this question? How much it grows with input size, or is that what it is? In relation to its input size? Okay, well, I'm gonna trust Google AI, I guess. So this one doesn't change, so I'm just gonna call it constant, and then we go through the length of the B string, and we just do this. These are O of 1 operations, nothing crazy, just conditionals and arithmetic and accessing of a list. So O of 1 inside of it, this is O of n, where n would be the B string, and then we go for I in range of the A string, and then we're just going to do the same thing. So this is O of 1, O of 1, and then if I is great, so that's O of 1, 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 and then this is going to be 27. So this is going to be 27 iterations at a maximum with some breakpoints early on in case something happens. So would this count as another n? I don't think it would, because it's constant. It's a constant of 27 too. So this would be technically, I think that would be constant because it's not growing as the input grows. It's just gonna be 27 loops every time. And then we do one more check. So this would technically, I'm pretty sure this is O of n. Or O of the length of STRA. Because STRA is going to be bigger. So I think that's the time complexity of this. And I think the space complexity is going to be... I think it's also O of 1, technically, because this is just going to be constant, right? And then that's the only thing that we're really changing. This doesn't change the size of the strings, it just changes them to be lowered, lowercase. Yeah. I don't know, maybe I'm being dumb. But I think this is O of 1, O of 1. It's just weird. It's very cool problem though, very cool problem. I'm happy I got to try this approach. I was looking, because in the what's it called? In the module, there was the stepping stone problem, and then the third one was determine if it's an anagram, and I remembered the valid anagram problem from that, so that's why I wanted to do this. But I don't know if it was better or not. I think it was very cool though, seeing the difference between them. So like how one does better than the other for smaller ones, and then the other one does better for the bigger ones. I actually want to try an even bigger one, like a really large one. Let's do 1,000. Let's do 1,000. And then I think I could lower this down to 500. I don't think it needs to be that big. Means, yeah. Okay, I might have made it. I don't know. I hope that doesn't take too long. I'm gonna just leave it on the side. Okay. So yeah, that's the problem. Anything else to talk about for it? I don't think there would be. I mean, I guess I could explain how I went about it. So, yeah, like I said, I handled the space by changing it to the character right after Z or lowercase z. Oh, never mind. Very cool. 550,000. So 5,000, 550,000. It's pretty cool. Uh, yeah. So we got Z, just incremented it. That's the character in it. Um, so if it's a space, then we just make it at the character, and then we just increment it like normal for the is valid anagram thing. This one is if the I is at a point where the sliding window is full, then we'll just remove the last element in the sliding window, so then we can go forward still. And then this one does something similar where it's like, okay, if it's full, then we're just gonna check if it's an anagram, and if it is, then we're returning true. And then we return false if it fails to find anything within this for loop. So yeah, that's the problem. As you can see, very varying results. Very cool overall. Yeah.